Hello everyone and welcome to this webinar hosted by CloudHPC and CFD FEA Service. This is Ruggero Poletto. I am the owner of the company, founder, and I'm here to welcome you all to this webinar. So let's quickly have a look at some information in order to take the most advantages out of the current webinar. You can all interact with me using a chat. I keep an eye on the chat, which is on my right hand side. So you can at any time ask for clarification or ask more details about a special topic I'm going to talk about. CFD FEA Service is an engineering company based in Italy, near Verona, founded in 2018, so this is our 4th year. And we do 3 main activities. We do software developments, in particular as far as engineering is concerned. We developed and we are the owner of the CloudHPC infrastructure, okay, and the infrastructure we're going to talk today. And obviously we do some consulting activities in particular for engineering design and for product design. Let's get more into the details about the CloudHPC. What is actually a CloudHPC? It's an IT infrastructure, so information technology, so computers in general, which allows people to run engineering simulation using a big number of hardware resources, okay? Cloud means that this infrastructure is made available to the people through internet, through the cloud, okay? The main advantage of this infrastructure type, so CloudHPC, is that allows you not to have downtime, so you at any time, you know the infrastructure is available for you to run your own simulation. You don't need to take care of the IT part. You just have to run your simulation. Any upgrades of the software installed, any new versions of the software, any new versions of the operating system, any problem with the security is automatically assessed by CFD FEA Service. So you don't need actually to take care of that. You can just focus on your business, which is run the simulation and get engineering information out of that. Thanks to the CloudHPC, you can speed up your simulation. Obviously, you can focus on your product because you just focus on the design of the product. Pay only for what you are actually using of the IT infrastructure and avoid the system setup. The infrastructure is ready at any time to be used for you. Today, the main topic is going to be scalability. Okay, scalability is the possibility to reduce the computational time required by the simulation to be completed, okay, by increasing the hardware resources we are going to assign to that simulation. The scalability can be defined into 2 different types. One is horizontal, which means if we want to run several scenarios of a certain simulation, we can run all the scenarios simultaneously. So in the time we usually are required to use in order to get the results of one single simulation, we can get the results of multiple scenarios at the same time. And then there is what I call the vertical scalability, which is the speed up of a single simulation. So we want this simulation, this single simulation, to be bigger and bigger in terms, for instance, of the mesh size, and we want to reduce the time required by our infrastructure, our HPC infrastructure, to actually compute the simulation and to provide us the results of that particular simulation. Okay, this can be done via a vertical scalability, and today we're going to talk a lot about this vertical scalability because it's the most important part we're going to see today. What actually means scalability? Scalability is a sort of parameter which is function of the time required to the system to get you the results. In particular, we can define the speed up, which is the time 1 divided by time n, where time 1 is the time required to the simulation to be completed when you run it using one single CPU. And Tn is the time required to the simulation to give you the results when you're using n CPUs. Okay, that is the speed up. Obviously, we can also define efficiency, which is the speed up divided by the number of CPUs used. Okay, so it's T1 time required to the simulation to be completed when performed with one single CPUs divided by n times Tn. So n being the number of CPUs used to compute that particular simulation. This is the efficiency. Okay, obviously we want the efficiency to remain as close as possible to 1 or to 100%, depending on how you consider that. And this is the speed up. Okay, we want this to be somehow proportional to n, to the number of processors we want to use. In fact, as we increase the number of processors, usually at the same time, with the same magnitude, we also increase the speed up. Okay, so if you use 8 processors, the speed up should be as close as possible to 8. This usually happens, but as we keep increasing the number of processors, the speed up tends to become flat, not to be proportional to the processors anymore. Okay, in this area in particular, it means that we are reducing the efficiency of our speed up methodology. Okay, obviously, what does the speed up depends on? A lot of things. Obviously, the software you're using, that's very important. At the same time, it's also very important the hardware you're using, and also the size of the simulation you're running. Okay, if you are running a simulation with 100 million cells, it's easier to get speed up with a higher number of CPUs compared to a simulation with 10,000 cells, okay, which is much smaller, and consequently achieving a good speed up is a little bit more difficult. Usually in the hardware made available also in the CloudHPC, there are two different approaches in order to achieve a speed up. There is the multi-core approach and multi-thread approach. Okay, if in your local computer you press Ctrl-Alt-Del, you can actually see if you have cores which allow you to get the multi-core approach, or if you have a logical processor which actually allows you to get the multi-thread approach. These are two different types of approaches in order to get scalability, okay, and they obviously depend on the hardware you use, but also they highly depend on the software you are using. Okay, not all the hardware have both these approaches available, and not all the software are able to use both these approaches. Okay, so you need at any time to be sure that the hardware you're using somehow matches the feature of the software you're going to use. I repeat, if you want question, if you have any particular request for clarification, just write a message in the chat. Let's have a closer look at the differences between the two methodologies, the two scalability methodologies we saw before. So the multi-core approach and the multi-thread approach. In the multi-core approach, we have a problem, which is our simulation. We divide this problem into sub-problems, okay? So we split actually the mesh into several smaller meshes, which, since they are smaller, they are easier and quicker to compute, okay? So each of these smaller meshes is actually assigned to one single core to be computed, to be resolved, and then in order to get the final solution, we need to merge all the results coming from the several cores into one single mesh altogether. Okay, so in multi-core approach, we split the problem, and then at the end, when the results is completed, we reassemble that. In multi-thread approach, actually, there is no split or reassembling, but all the threads, in this case, is a different name, but actually it's like the core we saw before. They are working simultaneously on the problem, somehow trying to be coordinated in order to to solve the problem, to find a solution to the CFD or FEA simulation we are actually running. Okay, obviously this second method is much easier, okay, because we don't need to split or reassemble the problem at the end, but there is a big but, is far less efficient. This first methodology, the multi-core approach, is way more efficient than the second approach, the multi-thread one. As I said before, not all the software have both approaches available, and now we're going to have a quick look at the situation we have in the cloud in terms of software installed and in terms of which of the approaches we saw so far are made available to the users. As we saw in the platform, we have Blender, we have Calculix, and we have CodaStar installed. And under OpenMPI, we have the multi-core approach. Under OpenMP, we have the multi-thread approach, okay? So for instance, Calculix only has the multi-thread approach. CodaStar has both the multi-core and multi-thread. This multi-core is in red because it's just made available to some of the versions of CodaStar installed on the platform, not all the versions installed. Then we have CodeSaturn, FDS, and OpenFOAM. These are three CFD softwares. They all have the multi-core approach, and FDS also has the multi-thread approach. I want to stress the OpenFOAM issue that only has the multi-core approach, okay? So far, in order to use correctly OpenFOAM, we were somehow not using correctly the hardware because the hardware we were providing was also multi-thread. But today we are going to also talk about the HIGHCORE new instance type, which allows to actually use 100% of the computing power, an instance type particularly designed for this situation. So for software where we have only multi-core approach and not multi-thread made available by the software. And then lastly, we also have Vento CFD. It's an Italian CFD software house, so particularly that designed this CFD software for civil and building purposes. And this approach, this software has available the multi-core approach only. So how do we actually how do we select the instance type? How can we disable or activate only the multi-core approach? Well, when actually launching the simulation, obviously we are selecting how many virtual CPUs we want to use, but at the same time, under RAM, we are selecting the RAM we want to make available for that particular simulation. We used to have only 3 different type of RAMs: high CPU, which allocates 1 GB of RAM per virtual CPU, the standard 4 GB per virtual CPU, and the Highman 8 GB of RAM allocated per virtual CPU. All these instance type are at the same time multi-thread and multi-core. So when using this instance type, you are actually allocating also multi-thread, which were not used by applications such as OpenFOAM. Last week we released the HIGHCORE instance type, which are allocated 2 GB per core. So no more per virtual CPU, but actually per core. So this means that under virtual CPU, the number you are choosing is no more a thread or a multi-thread or a logical processor, but it's actually a physical processor. You are allocating physical processor, as this instance type doesn't have multi-thread. It is only multi-core. So when running OpenFOAM or any other software which actually cannot take advantage of multi-thread, we recommend you to use this HIGHCORE instance, which is most suitable and actually designed to be used correctly by this type of software. The last selection regards the regular op slider, which is present here at the bottom. Is the last selection. This allows you basically in the CloudHPC platform. There are two different type of instances. One is regular and one is preemptible. Okay, when you are actually using a regular instance, you have a machine which is reserved to you for all the time required for the simulation to be completed. Instead, when using preemptible machine, the machine is not actually reserved to you, even if it's just used by yourself, is not reserved to you. So at any time, depending on how many people are using preemptible machine at the same time, this machine can suffer some reboots, some restarts. No worries, automatically the system attempts a new simulation launch automatically, so you don't need to do anything. Okay, and the simulation proceeds. You just need to pay attention because there might be some restarts in your simulation at some point. So pay attention on the way you configure OpenFOAM in particular. At the same time, preemptible machines, they are not compatible with all the software installed on the platform. Currently, we support FDS and OpenFOAM, which are by far, let's say, the most problematic software in terms of duration of the simulation. And obviously, there is a big advantage of using preemptible machine because they give you the opportunity to get a 50% discount on the cost on the equivalent machine that's using a regular instance type. As a connectivity, it is possible to connect at any time to the machine where your simulation is actually running using two methodologies in particular. One is the remote desktop, so VNC connection, made available directly through the web application, and the second one is a SSH connection. So if you have your private key, you can connect to the simulation via SSH at any time. You must be a little bit familiar with the terminal, with the Ubuntu terminal, but most of OpenFOAM users usually are familiar with Linux, so they shouldn't find problems with that. Other features, as I said, connectivity, API, Linux integration. Is possible to install this CloudHPC exec, a small software which actually allows you to launch a simulation directly from your terminal. And obviously, we have live support from 9 to 6 p.m. Central European time, summertime, so Rome or Berlin time zone. And basically, we can support you into actually complete and get the best setup for your simulation to achieve the best scalability. So let's have a quick look at the workflow. Obviously, you need to prepare your own simulation offline, so on your local computer. Once this is done, you can upload the simulation on the CloudHPC. Then you can select the number of virtual CPUs, which are available from 1 to 224, so a wide range of availability. You can select the RAM, and at the same time, you are selecting whether you want to use multi-thread or multi-core instances. And obviously, you need to select the version of the software, OpenFOAM, FDS, CodeStar, and many others. You need to select the versions of the software you want to use. Do you want to monitor your simulation? This is possible at runtime at any time. It is possible also to open ParaView or SmokeView to post-process the analysis that has been computed so far, or get feedbacks like convergence of the simulation, residuals, probes, plot, stuff like that. All these things are are generated or plot at runtime, so you can get really feedback as your simulation is actually proceeding. When everything is completed, obviously, you can download the results on your local computer and use ParaView or SmokeView or Salome or whatever to post-process and to view the results, to see the results produced by the simulation. Let's give it a try with the OpenFOAM. I prepared for you a case with SnappyXMesh already run. This case is the motorbike case, so taken from the tutorials of OpenFOAM. It's just a simple motorbike that's being run in the cloud using OpenFOAM. So let's go to the platform. The platform URL is cloud.cfdfeaservice.it. At the end of this presentation, we're going to see how you can register to get the information, to get an account on the platform, and to get to know actually how to launch the simulation. The platform mainly consists of two pages. One is the storage, in which we can upload or any new case by clicking here on the add button at the top right. We can drag and drop files of a case, or if there are multiple files, we can upload a compressed archive. In here, I previously uploaded the motorbike case over here. You can see it's a folder in here. I uploaded the whole case, so there is the 0 folder with the initial conditions. There is the constant folder with everything that needed to be done with the mesh information, basically. I'm opening that, and there is obviously the system folder with the numerical configuration of the simulation. As you can see, inside of the constant, there is the polymesh folder, which has been computed separately. And inside of the simulation of the system folder, there are all the data, FV schemes, FV solution, required for the simulation to run. So I go now under the simulation page. I press the plus button here at the top right. This allows me to run a new case, and here it is the menu we saw before. So I can pick any number of virtual CPU. I can select the core I want to use. As we said before, we have standard, high mem, and high CPU, which are different RAM sizes, but in all these three cases, we have multi-thread and multi-core instances at the same time. And then there is this HIGHCORE RAM, which allows you to get a multi-core only machine, so without the multi-thread, which is the best when using OpenFOAM, okay? Because as I said before, OpenFOAM is not a software which allows you to run multi-thread simulation. As far as OpenFOAM is concerned, we have a wide range of versions available, OpenFOAM 7 and 8 from the openfoam.org, and OpenFOAM 1912, 2006, 2012, and 2106 from the openfoam.com. At the same time, there are some customized solver made available in all these OpenFOAM solvers, but basically what you need to do is just select OpenFOAM 8 and make sure that you specified in your control dict file the solver you want to use, the application actually you want to use. This script OpenFOAM of OF8 actually detects the application you want to use from the control dict and actually run that particular application. So by pressing save, I'm launching the simulation, and here it is. The simulation is pending. Okay, as we see, is already running actually. In here we have a summary of all the choices we made. So script OpenFOAM.8 versions 8. The folder was motorbike for OpenFOAM 8, and the RAM was the HIGHCORE, so 2 GB of RAM allocated per core. This means that for this particular simulation, I have 16 gigabytes of RAM, so 8 times 2 gigabytes. So if now I press the I under view, I can get into the details of the running analysis. Usually there is not a queue when running the analysis, so when you actually pressing, you are actually launching the analysis, the simulation starts automatically. It just takes 3 minutes for the OpenFOAM to actually start. This is because the system generates a virtual machine for every simulation that is launched. Okay, so this let's say setup time in the beginning is just the time required to the system to generate this virtual machine where we are actually launching the simulation. So we just wait a couple of minutes together while the system actually defines this virtual machine, and so we get an idea of what happens when OpenFOAM is actually running, and also we can see how we can interact with the remote desktop, which is provided directly in this page. So we won't need to do anything else in particular, but directly in this page I can access the remote desktop to actually open the terminal, to see the logs, or to actually open ParaView, which is quite a common thing to do when OpenFOAM is launched. As you can see, step by step, the simulation is moving on. Now 1 more minute probably, and we'll be starting. So we just need to wait a little bit. Automatically, you see, the system has created a virtual machine where it is going to launch our analysis. So we just need to wait a few more seconds. So OpenFOAM will be actually launched on the system. Beside launching OpenFOAM, while we wait for this simulation to actually start, it is also possible to launch Snappy XMesh, which is quite common, let's say, mesh generators for OpenFOAM. So quite a few people using OpenFOAM at the same time are using Snappy XMesh in order to actually prepare the mesh for the OpenFOAM case. So if you want, you can just set up all your Snappy mesh generation files, in particular Snappy XMesh dict, and actually upload everything and launch the Snappy XMesh solver. The Snappy XMesh script. We are about to start the simulation now. Basically, the system has also downloaded the files from the storage, and here it is. The simulation is actually starting. All right. So if I now refresh the page, I will be able to see here at the bottom the remote desktop. I will be able to connect to the remote desktop of the instance where actually SimpleFOAM is actually running. This is the default solver made available by this motorbike case. So I can enter the motorbike case. I want to show you how to specify the solver. So under system control dict, under application, I specified the SimpleFOAM application, which is actually launched by the system automatically in here. As you can see, SimpleFOAM has been chosen as the solver to launch the simulation. Obviously, I can get a look at the log file, which is very quick. Obviously, the simulation is quite small, and at any time on the desktop, I can find ParaView to visualize the results. Okay, so if I just double click ParaView, let's see if I did that. I just need to refresh it. So if I double click ParaView, I can open my case, the system.foam file. I just need to remember to go under decompose case, and in here I can actually see the decomposed file, the solution at the current time step. So if I just run a slice, 1 second, let me pick the correct slice. Here it is. I have an idea of the flow across the motorbike. Okay, so using ParaView at any time, you can actually get an idea of the flow across the motorbike or the turbulence or any other variable which is actually calculated by OpenFOAM. Okay, like pressure. Okay, this is at runtime, so if I just refresh the time steps, probably I can go further on and see more advanced results. At the same time here, as images, I am proposed all the data which are actually produced by OpenFOAM, like the residuals or monitoring or any other informations like the cell max value, the maximum pressure and maximum velocity across my simulation. So let's move on. With the presentation. There are 1 or 2 slides. I see there are no questions, so no questions are coming. I hope I'm satisfactory for the explanations I made. Among the features, keep in mind that there are not just solvers. It is possible to run Netgen, SnappyX, MeshDict, like we said before, GMS stage, or it is also possible to run customized scripts. If you have a particular script for OpenFOAM, it is possible to run that. You need to create your account on the web application, but you need that account to be approved to run a customized script. So you need, let's say, a little bit of an advanced account. But just asking the IT, and they will make a quick check of your situation, and they can activate this particular feature to run customized scripts. Let's have also a quick look at the cost. Obviously, in this slide there is an error. It's not 8 GB per RAM, but it's actually 2 GB of RAM per core. But the main advantage of using HIGHCORE instance is the fact that you can save money compared to a multi-thread instance, which is not actually used by OpenFOAM. Okay, as you can see, this for the multi-core instance we have a price of 10 euro cent per core hour in this case. Or when using preemptible instance, is a 50% less, so it's 5 euro cent per core hour. So really a competitive price compared, let's say, to the market. And this instance is available, is particularly suitable for OpenFOAM, so it allows to save you a lot of money when running OpenFOAM on the cloud. So with this, my presentation is actually over. I invite you to take contact with me or with the company in general. This can be done at any time using the email addresses specified here. So info@cfdfeaservice.it or info@cloudhpc.cloud. They are both available whenever you want. So feel free to email us for any request of clarifications. Or if you want to register to the web application, to the CloudHPC, just visit the website cloudhpc.cloud. There is a register button, just fill the form you find in there, and after a few hours an account will be activated, and so you can start actually running your simulations on the cloud. Just keep in mind that to all the people who are going to register to the platform, they can get 300 virtual CPU hours for free, so 300 virtual CPU or threads or core, whatever they use, for free. So it's quite a good experience for you to start using the application and to get also a test of the app and to get, let's say, information on how can this be suitable for you. I see there is, thanks Fabio for the message. So there is one message in the chat. If no other messages are coming, I invite you all to register and to stay in touch with on our social networks. We are quite active on LinkedIn in particular, where we propose one webinar like this one every month. And so we stay in touch, and I hope to see you soon on the platform. Bye.